10 years to build the spacecraft, 10 years to get there, and now I think we will have more than 10 years to exploit all the science these people will dig out of this comet.
First results we had from Rosetta gave us an insight into the comet and comets in general, but now we're digging in with multi-instrument approach. Rosetta has said comets are much different than we expected, and so we really have decades of work to do.
The crazy, hectic work of the Rosetta operations were over. We now had time to focus purely on the science.
This was the first time we actually got to follow a comet around as it approached the sun and then went away again. So what we were really interested in was how does the interaction change?
We measured the noble gases, argon, krypton, xenon. The bulk of the terrestrial water is not from comets. But as they have a very high carbon content, a lot of organic molecules, they brought a huge amount of those, which may have sparked life finally on Earth. Glycine, the amino acid, shows that these prebiotic molecules actually exist.
One of the really cool things that Rosetta found was that you have seasons of the comet and how much the seasons influence the activity. That idea that seasons are very important in understanding comets is something we can apply to others.
We have observed 3 outbursts with almost all the instruments on the spacecraft, and that was a lucky event because outbursts are impossible to plan, to observe.
In some special cases, we see the correlation with some of the surface features like the cliffs or large water ice areas. Because since the first imaging, we were really seeing a large crack in that terrace region inset, and we were expecting it's collapsing, and finally we got it.
We see the coma is thousands of kilometers across, the tail is millions of kilometers long. And of course Rosetta is getting only in the very center of this, looking at the details and understanding the comet near the nucleus. We're still trying to work out actually how you link from the many fine structures of this sort of fine jets of gas and dust that Rosetta saw to how that links to the really large scales.
The mass of the nucleus is about 10 billion tons, and we have seen and found that the loss of mass was about 10 million tons, which is about 0.1% of the total mass. We found out that it's about 50% of that lost mass was released during 30 days before to 60 days after the perihelion.
We were on elliptical orbits, and twice a week we were getting really, really close.
It was a while that we were trying to really get this image where we could really see Philae on the surface without any doubt.
When you know where Philae is, then you can, by simulation, you know exactly where the wave went through. So this is what you are characterizing. And seeing the feet and the antenna of concert on a picture taken on ground was very important for us because it allows us to narrow down some data interpretation.
I can announce the full success of this historic descent of Rosetta towards 67P.
We got down to basically burying our nose into the comet dust.
We are still trying to understand what we saw. It's very interesting. It was not what we expected. We are still trying to understand the pressure. Probably the gas was not coming from straight down, but from some angle.
67P has been a really transformational mission in terms of the wealth and the high precision data that we've been able to get from this particular comet. But that doesn't mean that comet studies stop. Every comet that comes into the inner solar system is a precious source of information from the time before the planets formed.
We got all the wonderful images with the best resolution ever up to the very last moments. It's really a treasure chest to humanity.